Our next speaker in this session will be Grahame Vittorini, Technical Director at Quantinuum, and we'll talk about logical qubit applications with Quantinuum hardware.
Thank you very much. Thank you for the introduction, and thank you for the invitation and all the hard work by the organizers to put this together. I'll talk to you today about these logical qubit applications. Thank you very much to Jonathan, because he talked about some of the basics there. So when I breeze by them, for the people who aren't familiar, they won't be lost. So that's good. So I work for Quantinuum. We're a full stack quantum computing company doing both hardware and software. I work on the hardware end of things. Just to quickly also say, I'm only going to talk about current generation things and previous results. I'm not going to talk about any next generation stuff. So just to show you quickly, we have our quantum application stack here. At the bottom level, we have hardware, whether it's our own or other ecosystem quantum processors. On top of that, we have a full stack software as a service platform, which is cloud native, called Nexus, that lets you handle your projects, your circuits, your submissions, things like that. Above that, we have Ticket. Ticket is a software development kit, multi-platform and open source. Allows you to optimize circuits, compile them, transpile them, et cetera, for a variety of backends. And then we have applications on top of that. So some examples from us are the cybersecurity, quantum origin, quantum chemistry we have in Quanto, and we're working on some AI things. And then there are also ecosystem platforms other people are welcome to use, have their apps on top of our stack there. So the dark green is our stuff, and then there's some light green for other stuff. The other end is the hardware. We do trapped ions. I'm not going to go into great detail about that because this is a discussion about logical qubits and things like that, not about the hardware. And so there's a few things that are useful about our system. We have a robust coherence, two-level systems encoded into atomic ions. We have a flexible and reconfigurable system. We use mid-circuit measurement and reset and conditional logic. We have all-to-all connectivity. We don't have to, we can rearrange qubits as we need to, similar to what you saw from Jonathan, to get the interactions we need. We don't have to do nearest neighbor, which results in compounding infidelities. And we don't, and we have high fidelity zones that are isolated from each other. We can improve performance with sympathetic cooling, which means that our ions, our qubits are in the optimal state to get the best fidelities. And we also have not only normal sort of gates, we also have parameterized single qubit and 2-qubit gates. So that's the end of my hardware detail part. And I'll talk a little bit more about scaling quantum computing and things like that. So we're currently in the NISQ regime, so noisy intermediate scale quantum. A few noisy qubits are used for specialized algorithms to demonstrate quantum computing use cases. And we do need to move to a fault-tolerant or resilient paradigm, which allows us to actually scale these circuits up to do useful things at arbitrary depth and qubit number. And so to do that, we'll need to implement full quantum error correction and classical co-computing resources in a hybrid fashion. Can't just, we can't do lookup tables and things like that forever. And at Quantinuum, one of the ways we've helped address that is we've implemented a quantum error correction decoder toolkit that enables that a number of real-time hybrid QAC application demos. So first, I'm going to talk about that toolkit. That QR code, I think, goes to the right place. When it comes to this decoding, when we're dealing with quantum error correction, physical qubits are entangled to generate more robust logical qubits. And then you do careful state-preserving syndrome measurements on those logical qubits to detect errors and inform operations required to correct them. So we take something like this little flow diagram. You encode physical qubits, 7 of them in this case, into one logical qubit. On the left there, we can then do whatever operations, whether it's gating or idling, whatever the qubits do. After some time, you do a syndrome measurement to see if any errors have happened. After you get those results from that, you can decode it. So in that decoding, you determine the correction. That's where this, this real-time stuff comes into play. And then you can implement a correction. And the actual QAC decoding toolkit that I'm initially going to talk about happens in this decoding step here. As I mentioned before, initial demos, you'd look up tables and things like that, but that doesn't scale. Like you get to very, very large things and you just have these huge lookup tables. You can't process them quickly. You have to be able to programmatically do stuff. So this is a very simple diagram of this decoder toolkit. So the key thing is you might see that and think, oh, it's a bunch of decoders and things like that. It's not that. It's gives users access to a server-side hybrid compute environment to run their own user-defined decoding algorithms for their QAC workflows in real time. And so the customer defines the decoder in a low-level language. We recommend C or Rust, and then they compile that into a WASM binary. Apologies for the capitalization there. And then ticket, which is actually the quantum circuit, and the classical program, the WASM binary, is submitted jointly to our hardware, and then it all runs together. And there's this little diagram here, but there's a more detailed diagram on the next page, so I'll move to that. Typically what we do is you run through this step. You define your decoder in that low-level language in C or Rust. You do a unit test to make sure that everything's well behaved. You can then compile it into WASM. That gets added to your ticket, which again is the quantum circuit, and then you submit that where it's executed on a WASM virtual machine that is on a classical co-compute card that is part of the quantum computer. So all these steps are necessary to prepare for the proper decoding of your circuit. And we have some code snippet examples on that doc site, which the QR code goes back to. You can also just go to docs.quantinuum.com and navigate down to find that. And it has some examples there. Code snippets about all of these steps, but then it has example use cases like repeat until success, the 311 repetition code, and the Surface 17 code, including example code for that. And then I'm going to very briefly do this because mention this. There's a few restrictions. For example, like the program size for the WASM binary needs to be less than 6 megabytes for sure, and we recommend that it's less than 1.3 megabytes for best results. If you're using C, the standard C library isn't supported. On Rust, the Rust standard library is supported, but it'll result in bigger WASM binaries. And there's some things here about what kind of arguments are acceptable and such that are good to know if you're going to use this toolkit. But it's all on the doc site, as I mentioned. And I think they actually updated the doc site yesterday. I think independently of this presentation, just because there is some out-of-date stuff for it. So a few notes on this final note. So you can also do asynchronous WASM calls to minimize qubit idle time during the QEC cycle, so you're not effectively blocking with the WASM stuff and just causing your qubits to idle and build up error. These WASM binaries can be submitted and monitored via Nexus. So just as you'd submit your ticket, the WASM goes with it, and you can keep track of what's going on. WASM can be used with Quantinuum emulators to test your workflow. So it's not just, well, you have to run it on the hardware. It's like, nope, you can run it on the emulator. You can do your syntax checking. You can do your running on the emulator, and then you can go and run it on the actual machine. And then on current gen system, model 2, H2, which is our current gen of hardware, WASM decoding is single threaded. So that's another thing to keep in mind. So that's the quantum error correction decoder toolkit. Now I'm going to look at some applications where we use this. This is a tool that, of course, is available to our customers, but it's also a tool we use all the time for our demonstrations. So the first one is quantum chemistry. In the case of quantum chemistry, the problem with quantum mechanical systems, as many people know, is, for example, like the actual configuration space like is exponential in qubit number, or sorry, quantum mechanical, you know, in state space, et cetera, right? So like you end up that as you try and simulate small things, they're easy, but this exponential scaling starts to get you. You can see this on the right here, where you've got this table, and we're showing that for 16 molecular orbitals, you've got actually 18 molecular orbitals. You need billions. The state vector needs to be a billion elements, right? And it goes up by an order of magnitude when you add another set of 2 molecular orbitals. Typically, you need 2 molecular orbitals per qubit that's involved. So that's problematic. And then quantum computing helps with that because it's a more efficient way to store and process that. On top of that, we have quantum phase estimation, which is a very good algorithm for estimating molecular ground state energy with the appropriate circuit. And so our goal was to demonstrate end-to-end chemistry workflows involving phase estimation and error correction for the first time. This is not some groundbreaking result from a chemical like simulation. It's focused on, did we do all the pieces together end to end? So we used a single ancilla QPE algorithm, so quantum phase estimation algorithm. So it's an early fault tolerant algorithm. algorithm. We use the 713 color code, also known as the Steen code. So 7 physical qubits being encoded into 1 logical qubit with a distance of 3, so it can correct 1 error. And for non-Clifford gates, we used recursive gate teleportation. And then the actual thing we were trying to solve is super boring. It's an H2 molecule ground state energy. It's a 1 qubit Hamiltonian. But again, we're not trying to get some amazing scientific result. We're trying to show an end-to-end workflow. And so we use gate teleportation techniques for non-Clifford operators. We had a 22 qubit register utilizing up to 2,185 2 qubit gates and 760 mid-circuit measurements. And we obtained a chemically sensible energy estimate, which was off by 18 millihartz in 2,300 shots. And so we did find the real-time error correction improved the overall circuit fidelity in the process of doing this. And because this is coming out of this discussion about a decoder toolkit, like how does that come in? So this is showing the entire workflow here, and you get everything set up and then you get into this quantum phase estimation iteration cycle. And you can see it boxed there. You can see this natural flow of that. And under encoded back-end results, you're going to see decode and interpret the results. So we encode the circuits, we execute the circuits, we now need to get the results. And as we're doing that, we're checking for errors and things like that. And that's where the decoder toolkit is doing this work, checking for it, correcting for it, and then we can read out the results accurately. And so what does an encoded circuit look like? So we typically have 14 qubits for encoding the logical circuit, right? I said 713. We have 2 logical qubits. We need 14 physical qubits. And then there's 7 or more ancilla qubits. In this, we ended up using 8 based off some circuit decisions and things like that. And the logical circuit is super simple. At the top, you see there's 2 qubits. It does a few things. If we take that red box and we expand it, you see this encoded circuit with 21 qubits. And you can see there's a lot more going on from a physical perspective in order to do this the simulation. And so in the end, this is the actual data that came out of it. We ended up getting something which was at least chemically sensible. So like we said, 10 millihartz approximately was obtained. And you can actually see on the right where we're increasing the number of samples, and you can see the peak narrowing as we hone in. That dashed red line is the actual classically simulated result, and then the peak, finding the peak center is what we extract out as the quantum circuits result. And then looking on the left, effectively, we're showing a couple different, we're showing some results here of basically K is the precision of the energy estimate and like 2 to the K kind of deal. Well, 1/2 to the K with the precision. And then Q is basically a measure of infidelity. And so when we look at sort of, there's this no QEC result here, which is done with an emulator, showing that by say 12, we have almost complete loss of information. You can see there's an improvement by going with the error correction, both on the emulator, which is the blue upward facing triangles, and in the actual experiment with our hardware, which is the red downward facing triangles. So we see some improvement by using that quantum error correction, and we get a chemically sensible result. So that's that one. And the next one is code switching. I have no idea how much time I have, but I'm sure Dan will stand up and stand over there ominously, and I'll know. Okay, great. I'm actually doing really well. Okay, so code switching is the next one that we want to talk about. So, for example, a scalable fault-tolerant quantum computing gate set includes the T-gate, which is non-Clifford. And that T-gate can be used to prepare a magic state, which is a fundamental resource that we need to consume in FTQC, fault-tolerant quantum computing. There's 2 approaches to get that. One, Jonathan talked about, which is to generate a magic state or generate a state non-fault tolerantly and then distill it to increase the fidelity. This has a high resource overhead, right? Another approach is to generate a magic state in a code that allows for you to generate a transversal logical non-Clifford gate, such as the T-gate. So it's transversal, which means it's a lot easier to do, and you can do it by interacting physical qubits between 2 logical qubits 1 by 1, which is a lot more straightforward. and easier to execute and should be higher fidelity. And so you can generate it in one code, and then you can switch to a different code, which has a complementary set of gates, but can't easily run that T gate, let's say, and can't easily generate that magic state that you want. So what does that look like? This is sort of a diagram. This is the thing we're going to talk about. It's called code switching. And so you'll take something like this 3D triangular color code on the left, where you see, okay, it has a transversal C naught, it has a transversal S gate, it has a transversal T gate, but the Hadamard is not transversal. You've got another 2D triangular color code where C naught, H, and S are transversal, but T isn't. So you say, okay, when I want to do C naught, S, and T, I'll work in the 3D one. When I want to work in, when I need, H, I jump over to triangular, to the 2D one. I code switch over, I teleport the information over to that code. I do work in C naught HS, and I can jump back and forth. Ideally, you generate that T state and you're good to go, and you can just live in that other code, but you can continue to switch back and forth as you need to, though you'll be consuming logical qubits as you go. So the way we actually implemented it, so we start out showing again these two blocks between sort of that 3D diagram and that 2D diagram on the last one. These have specific codes that we're using. At the top, it's a quantum Reed-Muller code. It's a 1513, so 15 qubits, physical qubits become one logical qubit and can correct for one error. The one on the bottom is a Steen code, which is a 713, so 7 physical and 1 logical. And here are diagrams here showing those two codes in a plaquette sort of representation. And we can kind of ignore, there's some lines connecting them, we can ignore them for a moment. So when we actually go to encode these logical qubits, we're going to encode one of each. We're going to do that via repeat until success using flag circuits, and there's some pre-selection rate based on this. So I just mentioned that because later we'll have some acceptance rates, and you'll understand where that's coming from. It's from the preparation of these qubits with these flag circuits. And we use repeat until success, so we use the quantum error detecting toolkit to do this repeat until success successfully. Success. So it uses that. That's what this talk is about. And so we have 2D Z-type stabilizers, we have 3D X-type stabilizers, and we can actually, because effectively the bottom of that three-dimensional plaquette representation aligns with the, is like a projection effectively, like onto 2D down below, onto the 713. You can do transversal C naught between these qubits. So you can do a C naught between the 1 physical qubit in the 713 and the 1 physical qubit in 1513, and 2 and 2 and 3 and 3 and 4 and 4. That allows you to then do a C naught between those two code spaces just by using that sort of projection and connection. That's as much as you'll get out of me on that because I'm not an expert on these things, but there is some very beautiful geometry there that you can see. And so to actually send the information from one code to the other, we prepare a QRM code. The 1513, we prepare a Steen code. We generate the magic state via this T gate on the QRM, and then we do a single logical qubit teleportation using that transversal C naught and a measurement on the QRM, and then a conditional Z on the Steen code in order to teleport that T gate over to the Steen code. And now we have it over there, and we can go nuts with our C naughts and our H's and our S's. And you'll notice they both have transversal C naughts, which is an important aspect of this as well. Teleports logical T state between codes. So what is this actually? Here's sort of the results section or diagram. So this code switching result, which is 2025 Daguerre, and this archive it below, we got a fidelity of 5.1 times 10 to the minus 4 for the T state creation with an 82.58% acceptance. So creation, and then the fidelity of the final T gate in the Steen code was that 5.1 times 10 to the minus 4. That's about a factor of 2.7 lower than the leading physical error rate, which is dominated by spam. So it exceeds the pseudo threshold of the protocol. We have another result, which was a zero level magic distillation of 622, which is also on here. So I'll just mention it. I'm not going to talk about it in detail, but that was with an H state instead of a T state. And we had 7 times 10 to the minus 5 for that fidelity with an 85.2% acceptance. So that works a little bit differently. It doesn't have that fun teleportation and all that, but both very nice results on with code switching on one and that match distillation on the other. And so finally, I want to talk to you all about the last application, which is quantum memory. So we need to maintain quantum information with minimal loss during our idling time. So when no operations are being applied, there's a variety of ways that we can end up decohering. And some examples are coherent Z noise, as well as stochastic Z errors and other poly errors, and then finally qubit leakage. So ending up with population outside of the computational space of the qubit. So these can be addressed with a combination strategy. For example, a decoherence-free subspace, which you can think of as a 211 code, can be used to combat coherent Z noise. A repetition code can combat those poly errors, and then a leakage detection gadget can detect leakage, reset the qubit, and allow correction via QEC. And so ultimately, we want to break even on this next experiment or demonstration, which is to outperform the physical qubits using those that combination strategy above. So one piece of this is the decoherence-free subspace. Effectively, if you encode a state that looks like A01 plus B10, then what you'll find is that if you have Z, like if you have some Z source of noise, then whatever phase it wraps on them will end up being a global phase instead of some differential phase, and you just get to throw it away. Right? Quantum mechanics is great like that. So just throw it away. You've now protected your system from these sort of coherent uniform rotations. It's called decoherent-free subspace. And if we look at it as a code, if we use 0, 1 as the logical 0 and 1, 0 as the logical 1, you've got some stabilizers there. And then what's great is that you can then use what's called code concatenation to use an additional error correcting code on that decoherence-free subspace. What that means is that you replace all the stabilizers and polystrings on the larger code with the logical operators of the DFS code. So what you're seeing here, these states here and these stabilizers here, right? You can sit there and say, okay, like whatever my logical operations are and everything, I do these instead of physical operations. I do these on this decoherence-free subspace qubit instead. And then I just build an error correcting, a larger code on top of that. And that's concatenation. We can do this with a 5-qubit code, that's 513. When we do that, we end up with a 1014 code. So we get a distance 4 code, so it's a little better because it can do correction and some additional detection. So we put that together. We have a 1014 code. And the actual experiment was we prepped 2 things. We had some set of basis states, 0, 1, plus, minus, I, minus I. We prep those both in the logical basis and the physical basis, and we let them idle for a certain number of time. And in the case of the logical ones, every 2 seconds, we do a QEC cycle. So if an error comes in, then ideally the QEC cycle detects, corrects the error, and we keep going. And of course, we use the QEC decoder toolkit and the QEC cycle here or in that block. And then in the end, the fidelity of the memory channel is the average survivable probability over all states. We use this, we have 6 input states, right? So this is the actual output. I'm going to speak to the process fidelity. They say similar things, but I'm going to speak to the process fidelity. Process fidelity like goes down to 0.5, integrity goes down to 0. The point is you can see the structure that red is physical. So you see very quickly in like 2 seconds, you basically lose everything or whatever. That's a characteristic time scale. You have the 211 code, which is that decoherence-free subspace. It gives you an extension to, I don't know, maybe 10 seconds. And then the 1014 code, so that concatenated code, that's the dark blue. That gets you out much further, maybe to 15, 20 seconds, somewhere in there. But it also, there's a hit at the beginning due to the prep to get into that 1014, so you see a lower fidelity to start. And then one thing we added on was like, hey, right now we're not going to post-select. When we do add post-selection, we get a little bit of an increase in fidelity, but of course there's going to be an acceptance rate hit. So in the end, we wanted to break even. We encoded into that 1014 decoherence-free quantum error correcting code. We looked at the lifetimes between the QEC and the physical qubits, and we saw a 10 to 13x improvement in lifetime with no post-selection, and we saw of logical qubits compared to physical with no post-selection. and we saw a 20 to 25x improvement with post-selection. And so this is the conclusion slide. It just says all the results that we already had. We have the QEC decoder toolkit. We've used it for 3 different things. We got decent results, things that we're happy with. And thank you.